Welcome to my talk on a short proof of the Riemann hypothesis. So let me first of all talk about the Riemann's function, the Riemann Zeta function, and Hilbert's eighth problem, or the Riemann hypothesis. And the whole idea is to provide a constructive proof of what's known as the Hadamard-Weierstrass factorization of the psi function, and that's going to characterize the zeros of the zeta function. So let's just first of all quickly define the zeta function, zeta of s. For real s bigger than 1, it's just defined as the classic sum as n goes from 1 to infinity of n to the minus s, and then the related function, the psi function, which is essentially a regularized version of the zeta function. So psi of s is a half s minus 1, pi to the minus a half s, gamma over half s, and then the zeta function. And this is in some sense a regularized version of the zeta function, and you can essentially restate the Riemann hypothesis in terms of a condition on the psi function. So all the non-trivial zeros of xi of s are supposed to lie on the critical line real of s is equal to a half for RH to be true, or equivalently, as we've normalized or regularized, xi of a half plus is is equal to xi of a half minus s, and the zeros of that function are going to lie on the real axis. And one other formula that we're going to use is a formula due to Euler, a classic formula for the zeta function in terms of the product over primes of 1 minus p to the minus s for real s greater than 1. Okay. So let's first of all talk about the xi function. So we need to understand the zeros of the xi function, and then that'll tell us about the non-trivial zeros of the zeta function. So a classic book by Titmarsh on the theory of the Riemann zeta function provides a good summary of all previous known results. And so, for example, it's known that the xi function is an entire function of order 1. So it's known to have a Hadamard-Weierstrass factorization with normalization constants. So essentially equation 2. Xi of s can be written as this product. And of course we want to try and understand the zeros, which are given by rho. And again, as we've already said, the zeros rho of the psi function correspond to the non-trivial zeros of the zeta function. And if the Riemann hypothesis is true, then we know that the zeros of the psi function are all of the form a half plus I tau, where tau is real, and we know as we've regularized the zeta function, we have a symmetry condition that xi of s is equal to xi of 1 minus s. Hence the zeros will look like a half plus I times tau, and equation 2, if RH is true, will look something like this. Now, our short proof is going to depend on something called a generalized gamma convolution, a GGC distribution. This family distributions was due to somebody called Thorin, and his student Leonard Bonderson has written the classic text on it. And over the years, I've had many discussions with Leonard based on his GGC book, which is sort of a crucial book to have to understand how to actually go and find these Hadamard factorizations. So let's make an outline of the 3 steps to provide a proof of the Riemann hypothesis. So point A, this is known as Thompsons Condition. If you look at Leonard Bonderson's book on GGC, page 124, he talks about how the Riemann hypothesis is equivalent to a condition known as a generalized gamma convolution. So RH is equivalent to the existence of a GGC random variable denoted by h of a half of xi, whose Laplace transform expresses the reciprocal of the psi function. So xi of a half over a half plus root s is equal to Laplace transform of the random variable h. And a very important point is that that's only a real condition. We only have to show that for s greater than 0. So when you see the square root of s, I'm just taking the square root of a positive real. So at the moment, nothing complex about s. So this is known as Thompsons condition. So we'll first of all prove part A, which is due to Thorin. And then we need to go and construct our random variable h1/2 of xi. And we're going to do that in 2 steps. So point B, the first step is that we're going to start not by looking at xi at a half. Notice the half in there. We're going to start by looking at xi at alpha, where alpha is bigger than 1. And we're going to see that we can use that Euler product formula to construct a random variable h sub alpha of xi such that a Thompson condition holds for the case where alpha is bigger than 1. And that'll make us halfway there. And then from this, we'll then try and get to the half. And in order to do that, we'll prove the existence of a random variable, not evaluated at square root of s, but evaluated at square root of 1 plus s. And just to remind you, we're just going to consider s bigger than 0. So we'll use theorem 1 to prove theorem 2. And then we have to get to the Thompson condition above. And that essentially needs us to provide an analytical continuation of the zeta function to the line s goes from 0 to 1. And the way we do that is by something called Ramanujan's master theorem. For example, look in famous reference by Hardy. And so that will now allow us to evaluate not at the square root of 1 plus s, will allow us to evaluate at the square root of 1 minus s. And again, we're just considering a real s in our application of Ramanujan's master theorem. And you can see how equation 6 is used in the master theorem. It's used to evaluate these coefficients here on the right-hand side of Ramanujan's master theorem. So essentially 6 will get implemented here, and then Ramanujan's master theorem will allow us to do the analytical continuation to the piece of the line from 0 to 1. Of course, one question is, are the conditions of Ramanujan's master theorem holding true for the reciprocal xi function? This has been studied in a paper by Chowdhury and Kadir, I think 2012, who look at extensions of the Ramanujan-Hardy master theorem. And I think their example 5.2 and example 5.3 look at the reciprocal zeta function and show that essentially one of the analytical continuations or one integral representation in Titmarsh can be shown using this result, and the regularity conditions hold true. Same is true for the reciprocal gamma function, and putting those two together, we have the conditions for RMT to hold true for this reciprocal xi function. And actually, one other thing of note is that the tail properties of the reciprocal xi function are well known. There's something called the Heyman-Grossman bound, and the function on the right-hand side decays to 0 incredibly quickly. And so when we use something called the Fubini-Tonelli theorem to calculate the right-hand side of equation 7, the regularity conditions also hold for that true as well. Okay, so there's our three-step approach. First of all, let me talk about Thompsons condition and prove part A at the top, and then I'll prove part B, and then part C will then be used to go back up to prove Thompsons condition. Okay, so let's show part A. So 2 things to show. First of all, assume that RH is true. So from before, we have the Hadamard factorization given by 8. If we evaluate at s is equal to 0, we get the normalization constant of xi of a half. So hence we can write xi as the product in 9. And remember that Thompson condition is due to is a condition on the reciprocal xi function. So we get equation 10 that if RH is true, that the reciprocal xi function is the product over the zeros tau of tau squared over tau squared plus s squared. Now, a very useful identity that we'll see that we use when we look at GGC random variables is something called the Frulinelli identity. So that's just a simple integral identity. And if we take 10 and exponentiate we see that we can write 10 essentially in what's known as a GGC form. So the product of over tau squared plus s is an exponential of an integral of the log with respect to the measure u, and the measure u is just a sum of Dirac delta functions evaluated at the at those zeros tau. And one other thing to notice is that the measure nu that's sitting in here is a completely monotone function, is essentially just an integral with respect to the Thorin measure of the exponential function e to the minus tz. And equation 12 has essentially put the reciprocal psi function in what's known as Levy-Khinchin form. So it's well known that an exponential of minus the integral of 1 minus e to the minus s squared t times a measure dt over t can be written as a Laplace transform. And if we just replace s by square root of s, you can see that essentially we show that that Thompson's condition is true. So we've gone one way around. If RH is true, just by essentially direct calculation and Frulli-Nelli's identity, we can show that the reciprocal psi function satisfies Thompson's condition. What about other way around? Let's assume that Thompson's condition is true. And just to remind ourselves what's Thompson's condition, it's that the reciprocal psi function can be written as essentially a Laplace transform of a generalized gamma convolution. And remember that it looks like a very simple condition, which it is, but really the great power of Thompson's condition is that you only have to show that's true for s greater than 0. And just a little aside, an equivalent condition would be on xi over half over xi over half plus is, as written as a moment generating function of what's known as a symmetric extended generalized gamma convolution, which would be written as a scale mixture of normals where the mixing distribution is given by h. But we'll just focus on checking Thompson's condition as a Laplace transform. Excuse me. Now, we have to show that if Thompson's condition is true, that the Riemann hypothesis is true. Well, one of the great properties of a GGC is that the Laplace transform of a GGC is analytic in the whole complex plane cut along the negative real axis. So essentially the complex plane minus the interval from minus infinity to 0. So hence we know that by analytical continuation, we know that the denominator of xi over half plus root s can't have any zeros there. And so we know that if Thompson's condition is true, we know that xi over half plus s has no zeros for real s greater than 0. And so that means that xi of s has no zeros for real s greater than 0. And as xi of s is equal to, that's a minor typo, is equal to xi of 1 minus s, it has no zeros for real s less than a half either. So we know that all the zeros of xi over half plus s must lie on the line real s equals a half, which is essentially the Riemann hypothesis. Okay, so there's Thompson's condition. Again, let me just repeat the beautiful thing about Thompson's condition is you just have to check it for real s bigger than 0. And the nice thing about generalized gamma convolutions is that their Laplace transforms are analytical in the whole complex plane cut along the negative real axis. And this can be used not just for the zeta function, but for more general L functions. And if you Google a paper on Van Danzig pairs and walled couples and Hadamard factorizations, you can see this technique of GGC being used to a whole bunch of functions, hyperbolic functions, trigonometric functions, and of course here we're just going to apply it to the psi function. Okay, just one quick definition of the GGC. So as I said, the classic book on this is by Leonard Bonderson, called Generalized Gamma Convolutions and Related Distributions. Essentially, the Laplace transform of a GGC takes a form that looks like this. Remember that log of z over z plus s can be written in Frulli-Nelli form with respect to a Thorin measure u. So it's a special case of a Levy-Khinchin formula where the Levy measure is essentially written as a completely monotone function i.e. expected value of e to the minus tz over the variable t. So it's a very special case of a Levy distribution with a completely monotone Levy measure. Okay, so let's get to the next step. Remember part B. Part B is that we're going to start by proving an existence of a GGC distribution in the case where alpha here is bigger than 1. And the reason we start here is because we can just directly take the Euler product formula for the zeta function and essentially Binet's formula for the reciprocal gamma function, and just prove that it's in Levy form, and then prove again that you can find a GGC. So equation 13 will just be direct algebraic calculation, and essentially this is in Levy form. So this is essentially written as a Laplace transform with a Levy measure mu, and again direct calculation. Remember that there's an e to the minus alpha x that's also sitting in mu, which would hit this function here, and essentially we can characterize what the Levy measure is for the psi function. And again, this dates back to Khinchin in the 1930s, where he proved certain infinite divisibility properties and representations of the psi function as a Fourier and Laplace transform. Now, what's new is that we have to look at the reciprocal function, and what's new is that we have to find the Thoron measure. So we have to go from the Levy measure to the Thoron measure, and we'll see that that the reciprocal psi function satisfies again a Levy-looking formula, but now with an s squared in it, and now with a completely monotone function nu. And remember, completely monotone just means it can be written as an expected value over the measure u sub alpha of e to the minus tz. And we can explicitly find the Thoron measure in terms of the Levy measure. And again, remember that if Riemann hypothesis is true, this will essentially identify the zeros tau squared as well. So we actually have an explicit formula for the Thoron measure in terms of the Levy measure mu, which is given by 14 above. Okay, so let's just quickly see how we directly prove this, and again, mainly just algebraic calculation. So 17 and 18 are just definitions of xi of alpha and xi of alpha plus s. Taking derivatives, we can actually find the log derivative of the psi function. 20 then puts everything together, and notice that we're normalizing some of these functions. So we're adding the digamma function xi to normalize the gamma function, and remember that alpha is bigger than 1, so all these things are well defined. So essentially we have 3 terms in 20. The first term sitting here, the term that combines the gamma function with its little exponential discount factor, and then the term that's got the zeta function again discounted. And that will essentially give us a representation of xi of alpha plus s, or xi of alpha. We'll then take the reciprocal, and we'll find our Thoron representation. So we've got 3 terms each to treat separately. Again, why are we in this case just taking alpha bigger than 1? It's so we can just directly use the classic Euler product formula. So we use the Euler product formula, product over primes, and then it's just a question of writing this in Levy form. Okay, so 22 is just by definition of the zeta function of alpha plus s over zeta of alpha, and again notice that we're writing that in Levy form. If we add the exponential discount normalizing factor, essentially we're adding a linear term inside our Levy measure. And again, we can be explicit about the Levy measure. It's a sum over primes, a sum over r of log p, a Dirac delta at r log p of dx. If we combine terms, essentially we get a sum that involves a Dirac delta mass at log n with weights given by the von Mandergut function lambda of n over log n. Okay, so that deals with the first term. Let's deal with the next term. So how do we deal with the gamma function? Again, this is just a well-known fact. We can write this ratio of gamma functions in terms of essentially Binet's formula or Malmsteen's formula. And again, we know what the Levy measure is here for a gamma function. And then one final term, the term in front, can just again be directly related in 27 and 28 with a measure e to the x over delta of x, and don't forget that that gets hit by e to the minus alpha x, where alpha is actually bigger than 1. And essentially what we've used there is our favorite identity, Frullinelli's formula. Okay, so that's dealt with all three of those terms. Let's put it together. So essentially combining, essentially we've proved the first part of theorem 1, a representation for x psi of alpha plus s over x psi of alpha in terms of its Levy representation, and we've actually identified what the Levy measure mu is. And if you remember back to theorem 1, if I go all the way back to theorem 1, we've essentially proved 13. We now have to go and prove 15. So we have to look at the reciprocal psi function and essentially find this GGC random variable h. So how do we do that? So there's the first part of part B. So how do we find the reciprocal? Well, there are two very key identities that can be used for generalized gamma convolutions that let you switch between the two. And again, these are just algebraic facts. The more interesting one is equation 32, which essentially shows that this function here is a completely monotone function. And again, this will then appear in our Thorin measure. And again, you can see that up here, you can see where you can use equations 32 and equation 31. So they're just identities, and 33 is like a standard identity, essentially from the theory of Bessel functions. So again, remembering 31 and 32, they're very useful. Essentially, we can take our previous formula, rewrite it in terms of its Thorin measure. And again, if we wanted to, we could rewrite the linear term S again in terms of a Thorin type representation if we wanted to. So essentially, by combining 31 and 32 and placing it in here, and then taking the reciprocal, we've proved the second part of theorem 1. So let me be more specific. We've treated the case where alpha is bigger than 1, and we've shown the existence of a GGC random variable h sub alpha, and we've explicitly calculated what the Thorin measure looks like in that case there. Okay, so part B has been proved. The third and final part is just essentially consider the case where alpha is equal to a half. And essentially to do that, we need some form of analytical continuation. So we need to look at the Hardy-Ramanujan master theorem. Oh, and just as an aside, this little, let's call it a little trick that takes you from a Levy representation over here to a Thorin representation here, essentially applies to a wide class of functions. And essentially we can look at the reciprocal of a function f and write it as a Thorin measure. And 41 gives us this rather nice explicit characterization of the Thorin measure in terms of the Levy measure of the original function. Okay, so let's get to the final case, part C. And how do we construct a GGC construction for the Thorin case when alpha is equal to a half? And again, the difficulty here is that we can't just immediately apply the Euler product formula because it only works for real s bigger than 1. So first of all, we're going to change alpha to a half but we would still like the argument to be bigger than 1, so we're going to evaluate at the square root of 1 plus s. And so 42 is a modification of the previous theorem, and again there'll be a GGC random variable, I've called it h sub star of xi, such that this identity holds. And again, just to check, when you plug s is equal to 0, of course you get 1 and 1 on both sides. And again, the proof of 42 is really because the argument on the left hand side, a half plus square root of 1 plus s, is bigger than 1. Essentially we can still use the Euler product formula here. So essentially it'll be a same style proof. And again, let me just remind you, I'm only ever taking square roots of positives. We just only need to consider the case where s is bigger than 0. So again, 43 substitutes in. Again, just as before, we essentially have a product of 3 terms. Essentially we have to take each term separately. The first term we can just directly represent as a Thorin measure. So again, essentially Frullineri's formula. We can write the first term as a Laplace transform. We know exactly what the Thorin measure is. It's essentially a Dirac delta function evaluated at 3/4. So the first term is straightforward. The second term again, we'll use, we're going to evaluate at the square root of 1 plus s. So again, from before, we're just essentially going to use the Euler product formula. Slightly more, just ever so slightly more complicated than before, but we can deal with that integral in a similar way that we did before. The same thing is true of the gamma function. Again, just slightly more complicated than before, but essentially just algebra. And again, we can represent the gamma function. What are the two equivalent identities? Now we slightly modify our identities that provided the Thorin measure in B. So we have 52 and 53. So again, just correcting for these terms here leads to a simple correction here. And again, we can see in 54 we can write it as a similar integral. So we can go from the Levy measure to the Thorin measure. And again, how are we going to use that? We're going to use that to in 48 for the reciprocal zeta function, and we're going to use it in 51 for the reciprocal gamma function. So essentially, we're going to take 54, the term that comes in the Levy representation, and we're going to convert it to a term that essentially will look more like a Thorin for the reciprocal function. Okay, so putting that all together, and then remembering that we're evaluating at a half plus square root of 1 plus s, we essentially just by algebraic calculation have 58 and 59, and essentially there's a similar formula for the Thorin measure nu in terms of the Levy measure mu. Putting all that together, essentially we've proved 61, which essentially proves that the reciprocal psi function evaluated at a half plus square root of 1 plus s can be written again as a Laplace transform of a GGC random variable h sub star. And again, it's the same trick that was used in lemma 1 to go from the Levy measure to the new measure. And again, all such functions like square root of 1 plus s can be written in Thorin form. So essentially 63 is really just part B, theorem 2, but slightly shifted. So instead of evaluating at alpha plus root s, we evaluate it at a half plus square root of 1 plus s. And again, we get a Laplace transform representation of a reciprocal psi function. Now, why is that useful? So let's remind ourselves of Raman-Newton's master theorem. The previous result is useful for essentially calculating the coefficients that come into the expansion on the right-hand side to calculate the Mellin transform in Ramanujan's master theorem. And remember that Chowdhury and Kadir have shown regularity conditions for the master theorem to hold true. And remember that a Fubini-Tonelli result holds true because of the way that the Zeta function decays very quickly, essentially the Heyman-Grosswald bound. So one of the nice things is that you can replace those coefficients in the power series essentially using, if I pop back, essentially using equation 63 evaluated at s equals k will essentially give all those coefficients on the right hand side. And of course what we're aiming for now is an evaluation at square root of 1 minus s, and remember that s is between 0 and 1, and so essentially this provides our analytical continuation of the zeta function to the region from 0 to 1. The previous theorem essentially had already proved such a representation for s bigger than 1. And again, so replacing these coefficients with their Laplace transform using Fubini-Tonelli, just simply summing up the sum, calculating the integral, the gamma functions cancel. Essentially we've proved that xi of 3 upon 2 over xi of a half plus square root of 1 minus s can be written as a moment generating function. So expected value of e to the s h star of xi. That's a positive s, positive power in s, where s is between 0 and 1. So it's essentially an MGF representation. And then essentially we're going to exponentially tilt and replace 1 minus s by s, and then we'll be down to Thompsons condition. Okay, so here's how we get to Thompsons condition. Simply replace s by 1 minus s. So xi of 3 upon 2 over xi of a half plus root s. Excuse me. Remember that one of the key points is that Thompsons condition, we only have to check it for real s bigger than 0, so that square root of s is well defined. So essentially replacing s by 1 minus s, the expected value now becomes expected value of e to the 1 minus s times h star. Essentially this is an exponential tilt of the Laplace transform of the h star random variable. And one of the nice properties, if you look at Leonard Bondeson's book, is that the GGC property is preserved under exponential tilting as long as that integral is finite. But again, that finiteness is just given by our Ramanujan master theorem and the existence of the analytical continuation. So everything is nicely finite. Again, if you plug s equal to 0, I've got a normalization constant that comes from the exponential tilting. And so the xi of 3 upon 2 cancels, and the xi of a half can get put over the other side, and hence we've checked Thompsons condition. So we've shown the existence of a GGC random variable such that the reciprocal Zeta function, so xi of a half or xi of a half plus root s is equal to the Laplace transform of GGC. Another way of saying that is that the function on the left-hand side is what's known as a hyperbolically completely monotone function. So essentially we've checked Thompsons condition, and essentially as Thompsons condition is equivalent to the Riemann hypothesis, essentially we've shown that all non-trivial zeros of the zeta function lie on the critical line, a half plus is. Remember that a GGC, the Laplace transform of GGC, is analytic in the whole complex plane, taken out the interval minus infinity to 0, and that was enough to prove the Riemann hypothesis. Thank you for listening. I'd also like to extend my gratitude to Leonard Bondeson over many, many years of many email discussions. It's been a great pleasure to have read his book and discussed things with him. And I'd also like to thank Jialun Zhu for many discussions on the problem. And thank you for listening.